So this video is going to walk you through two equations and one system, if you will, in thinking about how your blood is buffered. Okay, so the first equation I want to put on the slide here is the equation that we've already learned about that talks about fuel metabolism. So any basic fuel combines with oxygen in a one-way reaction to generate carbon dioxide, water, and energy. And so that's our basic fuel metabolism equation. We'll expand on that throughout this course here, but that's the base equation that we've sort of learned about. A metabolic process that we're going to talk about is breathing. And although there's lots of different aspects to breathing that are important, for right now, here's what we're going to focus on for breathing. The purpose of breathing in our context is to focus on bringing oxygen in and carbon dioxide out. Well, here's why this is important. If we think about really what oxygen is a reactant in this basic fuel equation. So we can think of it sort of being a nutrient, if you will, that it's bringing in. Similarly, we can think about carbon dioxide as being a waste product that the purpose of breathing is to get rid of. So this is going to be waste that's thus taken out by the process of breathing. So some of the terms that we're going to see throughout this course are going to often have common prefixes or suffixes to them. In this case, I want to introduce prefixes that we're going to see when we refer to our ventilation state. And what do I mean by that? Well, with regards to breathing, are we breathing less than we should be or more than we should be? And so these prefixes that we're going to see are hypo for less than or hyper for more than. And so if we think about what happens in both of these situations, when we are hypoventilating or breathing less than we should, that means we are taking less oxygen in, but we're also taking and putting less carbon dioxide out. And fundamentally what this is going to mean is that oxygen levels in our system are going to be lower, but carbon dioxide levels are going to be higher. Converse of that is when we're hyperventilating, we're having excess oxygen that comes into our system, but also excess oxygen or CO2 that's exhaled out. So again, that's going to mean that we are going to have lower levels of carbon dioxide in our body than we would normally have under normal respiration states. Okay, so equation that we've known with fuel metabolism, process that we're learning about with breathing, and for our context here, the main purpose of breathing is to take oxygen in and eliminate CO2. And a new equation that we're going to learn about here is an enzymatic process. And so that enzymatic process is going to take water and combine it with gaseous carbon dioxide in a reversible process to generate carbonic acid. And this is really important because carbon dioxide as a gas would be very problematic in our bloodstream. We can't have gas bubbles in our bloodstream. So this process is handled by an enzyme, and that enzyme is abbreviated CA, and the enzyme's name is carbonic anhydrase. And speaking of suffixes, prefixes like hyper and hypo, and suffixes like ASE. Anytime you see ASE, know that that's referring to an enzyme. So carbonic anhydrase is an important enzyme in your body that's going to allow you to solubilize CO2, take it out of the gas form and put it in carbonic acid form, or regenerate CO2. And we're going to see how that comes into play when we learn about how hemoglobin transfers oxygen in your bloodstream. So we're going to learn about that whole process. But a second part of this equilibrium is understanding that carbonic acid is a weak acid, and remembering that weak acids dissociate to generate H plus and then their conjugate base. Carbonic acid so does the same. A number that I need you to know is that the pKa of carbonic acid is 6.35. I want you to remember that. And then when we think about, again, dissociation is going to generate H plus and then bicarbonate ions. So in essence, what carbon dioxide allows us to do is toggle carbon dioxide between a gaseous form and a solubilized form. Okay, so just putting a few other pieces on here, remembering that this is carbonic acid. I want you to remember the name of that acid, weak acid. Again, pKa is 6.35. So what we're going to do now is map on and understand sort of how all three of these processes kind of talk to one another. So I'm going to start over here on the right, and I'm going to talk about what happens if you were to be hypoventilating. So when we think about hypoventilating, what's going to be happening here is we are going to have, as we highlighted, decreased levels of oxygen that are coming in, but importantly for this context, we are going to have decreased levels of CO2 that's going out. What that means is we are going to have elevated levels of CO2. Let me put that in orange here. Elevated levels of CO2 are going to be happening when we are hypoventilating. Hypoventilating is going to increase concentrations of CO2. Now, I know one of the things that we talked about and you learned about in general chemistry is how equilibria can shift. We learned it as Le Chatelier's principle, but one of the things I want you to remember is that push-pull analogy that we talked about. So when we talk about pushing, that means we're adding in a reagent. And notice I don't always say reactant because a reagent can either be a product or a reactant. When we add something in, we are going to push the equilibrium to the opposite side. When we pull on a reactant or a product, a reagent, when we pull on a reagent, that means we're going to pull the equilibrium towards that side. So in this situation, when we are hypoventilating and we're increasing CO2 concentrations, it shifts this equilibrium to the right. So what that is going to mean is that we are going to have elevated levels of H+, and that is going to mean we are in a state of acidosis. Elevated levels of H+, decreased pH, a state of acidosis. So over here on the right, I'm going to highlight that that is going to put us in a state of acidosis. And we refer to this as respiratory acidosis because it is a product of suppressed respiration, a low respiration rate, hypoventilation. Okay, let's take the flip side maybe a little bit more quickly now. Let's talk about what would happen if you were hyperventilating. Well, hyperventilating is now going to have the opposite effect. Since we are increasing our exhalation of CO2, that means we are going to be decreasing the concentration of CO2 that we have in our body. Now we're pulling on that side of the equilibrium, so we're going to shift our equilibrium to that side, to the side with H2O and CO2, which means we are going to be decreasing the concentration of H+. And in that case, decreasing H+ concentrations means increasing pH. That is a state of alkalosis. And again, this would be respiratory alkalosis. Okay, so an important thing to recognize is that your breathing, in affecting your carbon dioxide levels, can affect your blood pH. Okay, so kind of summarizing that up here, we can have increases or decreases in carbon dioxide concentrations. Okay, and that is going to shift our equilibrium to either increase or decrease our H+ concentration and correspondingly the pH, and so this is going to affect blood pH. So we're going to see this come into play when we talk about our aspirin overdose case study. Fundamentally, what's going to happen when somebody overdoses on aspirin is it induces a state of hyperventilation. So that hyperventilation will put them into a state of respiratory alkalosis, so elevated blood pH, and you have to find a way to treat that. So two other little pieces to kind of like map on here, things that I'm just going to mention superficially because we're not going to get into details of it later, but you'll see that there's another place where we have carbon dioxide in this process. We see carbon dioxide generated as a waste product from fuel metabolism. So not only is carbon dioxide something that plays in with our respiration state, but that carbon dioxide again is generated from fuel metabolism. So this is going to be a process of metabolic, either acidosis. If we're talking about elevated CO2 levels, we're really not talking about decreasing CO2 levels through metabolic processes, but that process of introducing more carbon dioxide by fuel metabolism is a way to contribute to an acidotic state through metabolism. As we'll learn about, there's lots of other metabolic processes that might contribute to a drop in blood pH, and that's going to be a state of metabolic acidosis. One other little piece here. So again, these pink and purple parts are really things we're going to get to later. But when we think about muscle contraction, and ultimately the hydrolysis or the use of ATP, the hydrolysis of ATP increases the concentration of H+. So again, another way that we can contribute to an acidotic state. And as we'll learn about when we learn about hemoglobin and oxygen delivery, we'll learn about how all of these processes talk to one another to have a positive sort of feedback loop to indicate, hey, my muscles are working really hard. I need to bring in more oxygen to support that process. So we're going to see this blood buffering system set of equations again when we learn about how the hemoglobin highway works.